What if I told you two models, same architecture, same size, same training budget, could produce wildly different results? Not because of better algorithms. Not because of more GPUs. Because of the data. This is the garbage in, garbage out problem, and it's the single most important lesson in modern AI. In 2025, the research community proved something remarkable. A 7 billion parameter model trained on carefully selected data matched models trained on 6 times more data. 6 times. The model didn't get smarter. The data got better. This is the hidden science behind every top-tier LLM. It's not just about scale anymore. It's about what you feed the model. In this video, we'll walk through the entire data engineering pipeline, from raw web crawls to the final curated dataset, and show you why data quality has become the single biggest lever in AI performance. Every LLM starts in the same place, the open web. The backbone of virtually every training run is CommonCrawl, a non-profit that's been archiving the internet since 2008. Every few months, they release a new snapshot of roughly 3 to 5 billion web pages. That's about 50 to 80 terabytes of compressed HTML. But CommonCrawl is just the starting point. Think of it as crude oil. You wouldn't pour crude oil into a car engine. You refine it first. Beyond the web, there are 3 other major sources. Books, digitized collections like Books 3, academic papers from AR14 and PubMed. Code, billions of lines from GitHub repositories, collected in datasets like the Stack and StarCoder. And then there's Wikipedia, social media, and specialized scientific sources like Semantic Scholar. Each source has different characteristics. Web data is noisy but diverse. Books are well-structured but limited in volume. Code teaches logical reasoning but is highly repetitive. The art is knowing what each source contributes. Here's what's fascinating. When Hugging Face built their FineWeb dataset, they started with a single CommonCrawl snapshot. After their full pipeline, filtering, deduplication, quality scoring, only about 20% of the original data remained. But that 20% contained nearly all the learning signal. The raw ingredients matter. But how you process them matters a lot more. Here's a shocking number. When researchers processed raw CommonCrawl for the C4 dataset, exact deduplication removed 30 to 50% of all documents. Think about that. Half the web is copies of copies. Duplicate data causes 3 big problems. First, training inefficiency. The model wastes compute learning the same patterns multiple times. Second, memorization risk. Duplicated text gets baked into the model's weights, which is how you end up with an LLM that can recite entire web pages verbatim. Third, benchmark contamination. Benchmark questions often appear in multiple web sources, so the model effectively sees the test answers during training. There are 3 levels of deduplication. Exact dedup is the simplest. You hash every document using something like SHA-256, and any 2 documents with the same hash are identical. Fast, but it misses near duplicates, like the same news article published on 10 different sites with minor edits. That's where minhash comes in. Minhash creates a fingerprint by breaking documents into shingles, overlapping chunks of text. It then finds the minimum hash value of each shingle to create a compact signature. Documents with similar signatures are likely near duplicates. This catches those slightly edited copies. And then there's n-gram dedup. Instead of removing whole documents, it removes repeated spans of text, like paragraphs that appear in thousands of different contexts. Google C4 used this at the sentence level. The impact? Removing near duplicates from the pile reduced GPT-2's test perplexity by 0.2 to 0.3 nats. Not because the model learned less. Because it stopped memorizing test data it had already seen. After deduplication comes quality filtering. This is where the real magic happens. The pipeline typically works in 2 layers. Layer 1 is cheap heuristics, fast rules that every document passes through. Length filters remove anything under 50 words or over 100,000 words. Symbol-to-word ratio catches pages that are mostly menus, ads, or emoji-filled nonsense. Language detection, usually a fast text model, filters to your target language. C4's English filter kept only about 30 to 40% of CommonCrawl. Boilerplate removal strips navigation bars, sidebars, and comment sections. There's also perplexity filtering, using a small language model trained on Wikipedia to score each document. If a document has unusually high perplexity, it's probably not well-written text. These heuristics are fast and effective. They can process terabytes of data in hours. But they're crude. They can't tell good writing from bad writing. That's where Layer 2 comes in, model-based classifiers. In 2024, Hugging Face released FineWeb-Edu. Here's what they did. They took a Llama 3 8 billion parameter model and trained it on 500,000 human-annotated web pages. Each page was scored on educational quality from 0 to 5. They then ran this classifier over their entire 15 trillion token FineWeb dataset. The result was stunning. Only 8% of web pages scored 3 or higher, meaning only 8% was considered genuinely educational. But those pages contained most of the learning signal. DataCompLM, or DCLM, took a simpler approach. Their winning submission used a fast text classifier trained on just 200,000 examples. Nothing fancy. But the results were extraordinary. A 7 billion model trained on their 2.5 trillion token dataset achieved 64% on MMLU. That matched models trained on 6 times more data. Quality filtering isn't just a nice-to-have. It's the difference between a good model and a great one. Once you've sourced, deduplicated, and filtered your data, you still have a critical decision. How do you mix the ingredients? This is the recipe problem, and the difference between Llama 1 and Llama 3 shows how much it matters. Llama 1's data mixture was 67% web pages, 15% books, 4.5% code, 4.5% Wikipedia, and 4.5% academic papers. Llama 3, just 2 years later, shifted dramatically, 50% web, 25% books, 15% code, and 10% academic sources. Notice what changed. Code went from 4.5% to 15%, more than tripled. Books went from 15 to 25%. Why does code matter so much? Because code trains models in logical reasoning, structured thinking, and precise instruction following. Code has a naturally high signal-to-noise ratio. Every line either compiles or it doesn't. Every function either works or it breaks. This is why Llama 3 has such strong coding abilities despite not being a code-specific model. The data recipe was built differently. Some labs take this further with curriculum learning, ordering the training data by difficulty. Early training uses Wikipedia and books, clean, factual, well-structured. Mid-training mixes in web data and code. Late training introduces more diverse and noisier sources. The sequence matters almost as much as the mixture itself. Here's where things get weird. What if the best training data isn't human-written at all? In 2023, Microsoft released a paper called "Textbooks Are All You Need." They generated 600,000 synthetic textbook chapters and exercise pairs, none written by humans. Then they trained a 1.3 billion parameter model called Phi-1 on this data. That tiny model matched models 2 to 5 times larger on coding benchmarks. It scored over 50% on human eval, approaching GPT 3.5's performance with a fraction of the parameters. Then came Cosmopedia from Hugging Face. They used Mixtral 8x7b to generate 30 billion tokens of synthetic textbook-style data. A 1 billion model trained on this approached the performance of 7 billion models. And in 2025, DeepSeek took this even further. There are one model used pure reinforcement learning, no supervised data at all. The model generated its own reasoning traces and learned from them. No human-written examples required. The promise is obvious: synthetic data is cheap, unlimited, and can be tailored to specific domains. But there's a dark side. Research by Shumilov and colleagues in 2023 showed something alarming. When models train on their own outputs, they suffer from model collapse. Diversity shrinks. Errors compound. The model gets stuck in a self-reinforcing loop of its own mistakes. The fix? Mix synthetic data with real data. Use diverse generator models. And never let a model train exclusively on its own outputs. Synthetic data is a superpower, but only when used carefully. Let's talk about the numbers that changed everything. FineWeb-Edu. Hugging Face took their 15 trillion token FineWeb dataset and applied their educational classifier. They kept only the top-scoring 5 trillion tokens. 5 trillion versus 15 trillion, one-third the size. On every single benchmark, every one, FineWeb-Edu performed better. A model trained on 5 trillion high-quality tokens beat a model trained on 15 trillion unfiltered tokens. 3 times less data. Better results. Then there's D4, the data diplomacy dataset. Just 2 trillion tokens. When researchers trained on it, they matched the performance of Red Pajama at 30 trillion tokens. That's a 15-to-1 reduction with zero performance loss. And DCLM. A 7 billion model trained on their 2.5 trillion token baseline scored 64% on MMLU. That matches Mistral's 7B. It exceeds Llama 2's 7B by nearly 20 points. Same architecture. Same size. Better data. These aren't edge cases. They're the settled science of modern LLM training. Let me restate that more simply. If you take a dataset, clean it aggressively, and remove most of it, you get a better model, not a worse one. The noise was holding you back the whole time. So how do the biggest labs actually handle data? Meta is the most transparent. For Llama 3, they used a multi-stage pipeline. Exact dedup, then min-hash at a 0.8 similarity threshold. Then they used Llama 2 itself, the previous generation model, to score the quality of every document in their corpus. Running an LLM over billions of documents is expensive. Meta decided it was worth every GPU hour. They also removed any page that overlapped with common benchmarks. If a web page contained a known test question, it was discarded. DeepSeek goes even further. They do document level, paragraph level, and line level deduplication. For math and reasoning content, they use embedding-based near-dedup, not just min-hash, to catch near-identical mathematical derivations. OpenAI is more secretive, their exact pipeline is proprietary. But we know GPT-4 used multi-stage filtering with both heuristic and classifier-based methods. And for their O1 and O3 models, they generate synthetic reasoning traces, having models practice step-by-step reasoning and using those traces as training data. The common thread? Every major lab now treats data curation as a first-class engineering problem. Not an afterthought. Here's the bottom line. The era of, just add more data, is over. The science is settled. Data quality beats data quantity, every single time. A 5 trillion token dataset that's carefully curated outperforms a 15 trillion token dataset scraped from the raw web. A 2 trillion token gold standard matches a 30 trillion token web dump. If you're building an LLM, whether it's a 1 billion parameter model for a specific task or a frontier-grade system, spend more time on your data pipeline than on your architecture. Choose your sources deliberately. Deduplicate aggressively. Filter for quality. And mix your ingredients with intention. The model is just the engine. The data is the fuel. If you found this useful, like and subscribe. And check out our other videos on LLM architecture, training techniques, and the latest AI research. Thanks for watching.